Hello everybody, and welcome to another video on my channel. Today we will be doing a math video, and I'm sorry since it's been a very long time since I've actually done one of these videos because I had taken a break. I got a new iPad and stuff, and I hope you notice a quality improvement in these next couple videos from my older videos since I'm recording this on a device with a better screen, etc, etc. That's really about it. Without further ado, let's move on to the video, and I guess that's about it. Simson's rule is one of the approximations used to approximate integrals. Obviously, it's an approximation, but it's not just one rule, it's multiple types of rules. So there are a couple of rules involved when approximating integrals like this using Simson's rules. The first type is the 1/3 rules. These rules are very essential and often taught in many elementary calculus courses because they are very useful for approximating quadratic functions, and in fact they do this with perfect accuracy. Next up, there are the 3/8 rules. Now the 3/8 rules are used to approximate cubic functions, and they perfectly approximate cubic functions. Now this is not a really good drawing, but you get the point. Oftentimes, the 3/8 rule will be more accurate than the 1/3 rule, or rules in this case, because there's some things I haven't talked about, which I'm going to talk about very soon, because it uses more points and a more defined coefficients. Also, this difference comes from the derivation of these different formulas and rules. The next classification of rules that can happen is the composite rules. The composite rules basically involve using a different number of subintervals, which was covered in my last videos. And if you haven't seen those, please make sure to go watch those, as they really help out my channel and they'll give you an essential primer for this video. Composite rules are, of course, as I said earlier, have a more amount of subintervals, but the thing is they can be variable. So over here, we can write down composite rules, and these, instead of having just 1 or 2 or 3 subintervals like the simple rules I'm about to show you, these composite rules have a variable number of subintervals and step size in that case, because the step size, of course, is b minus a divided by n, where n is the number of subintervals. So since you have a variable n in this, oftentimes these will be more accurate when approximating functions and values that are not oftentimes, since it's a variable number of subintervals, these will be far more accurate as we can change them, especially when it comes to approximating things like the natural logarithm function, ln x, e to the x, the exponential function, any other arbitrary exponential function, and many more. But with the 1/3 rule, in fact, the composite function will still be able to approximate a parabola perfectly, just like the simple 1/3 rule does. The same thing also applies with the 3/8 rule, where the 3/8 composite will also have the same accuracy for cubics, that being a 100% accuracy rate, compared with the regular rule or just the simple rule. All of these, in fact, go within a simple classification of the closed form of something called Newton-Cotes rule. These rules involve approximating different levels of quadratics with different levels of accuracy. So, in fact, you might have seen some of them before. If you watched my last video, you would realize that the trapezoid rule is actually one of them. Now, of course, not everyone might know the trapezoid rule, and that's what was covered in my last video, but let me write down the simple list of the different rules that involve these closed forms. These 4 rules comprise different levels of accuracy for different quadratics. Sorry, not quadratics, for different functions or order of polynomials. For the trapezoid rule, the order would be 1, where it would give deliver perfect accuracy. Basically, it could do 100% accuracy for linear functions. For Simson's rules 1/3, it would be degree 2 or quadratic functions. For the 3/8 Simson's rule, it would be cubic functions. And for the final Boole's rule, you can get where this is going. This would be quartic functions or degree 4. But we will not cover Boole's rule over here and many other advanced forms, as the derivation of this is very complicated and even the application can get much harder, oftentimes involving knowledge of infinite series. Now, some of you who might have seen my videos before might ask, well, is there going to be a derivation for this, or did people do it around just by guessing? Actually, there is a very accurate and rigorous derivation where it basically is called interpolating functions. Basically, you take the integral of a function, then you process it through a bunch of operations, and it spits out an approximation for the integral for the area, basically just the integral or the definite integral of a function of that value. So Simson's rule the 1/3 would be described by interpolating a quadratic function, and so on and so forth. But since we do not have knowledge of integration, this will not really be necessary for now, and I will include a derivation video in the future when we've covered integration. That's really about it for the different types and understanding of Simson's rule, because I think it was very necessary to do that so you know a lot of the background information on how each of these was developed. But because, of course, this is not just about teaching you stuff, this should also be about creating your own thoughts, your own habits, and trying to act upon them and trying to make you curious. Today, though, we will only be learning the composite form and the simple form of the 1/3 Simson rule. So, let's go on to that. Over here, I have a blank page, and let's get started. Simson's rule for the 1/3 form or 1/3 variation says that the area under the curve is approximated by b minus a over 6, where a and b are the endpoints of the interval we're approximating the area upon, of f of a plus 4f of a plus b over 2 plus f of b. This formula only involves 3 points, yet it can somehow perfectly approximate a quadratic, and that's something which is very interesting. Now, you might be confused why there's a b minus a over 6, and if I bring it into another form, it might become a little more clear. So over here, we have the next formula, and you might notice that b minus a over 2 looked a little familiar. That is because it is the formula of b minus a over n, where n is equal to 2. So essentially, this is having 1/3, which is a coefficient. That's not very uncommon. That was also in the trapezoidal rule. But instead of having the 1/2, we have the 1/3 coefficient, and we have b minus a over n, where n is equal to 2. And the reason because of that is because if we have 3 points, if we draw a quick graph over here, and we have 3 points along the function, we have a starting point over here, which you can say A, then the ending point B, and then at the midpoint, we would have A plus B by 2, or the midpoint, so we can just call this M. And since this says the size of the step, and the amount of steps where n is equal to 2, there are really only 2 steps, from A to M, and then from M to B. Now that you know the formula for the simple rule, we can move on to the formula for the compound rule. The composite rule. The composite rule's formula goes as such. The formula of the area of Simson's composite rule with the 1/3 variation goes as follows. The area is approximately b minus a divided by 6 multiplied by f of a plus, then we have, b minus a by 3n multiplied by f of a plus 4 multiplied by f of a plus the step size, so a plus b minus a over n, and then plus 2 multiplied by the function times a plus 2 multiplied, so 2 multiplied by b minus a over n, which is again twice the step size, so we're moving forward. And then this repeats 4, 2, 4, 2 until we go to the end where we have 4 multiplied by the function of where the value of x is b minus 2 to b minus a over n, then plus 2 multiplied by f, b minus just b minus a over n, and then plus f of b. Now, this is not much more complicated, but it provides a lot more accuracy when it comes to approximating other functions that are not quadratic. In this video, we will be doing 2 examples, and the first example, we will be using the simple rule to approximate the area of a quadratic perfectly, and I know by integration that it will be correct, and because I've done the problem that I'm going to show you before. The next problem that we will have will be one where we approximate a cubic function using the composite formula for a certain number of subintervals and as the interval that we're evaluating over just specified by me. So let's move on to these examples. Over here we have an example which says approximate the area under the quadratic x squared plus 2x plus 1 from 0 to 2. As I specified earlier, in this problem, we will be using the simple form or just the really the simple form. There's no really name for it. Some people just call it the Simpson's 1/3 rule and call the composite form the composite Simpson's 1/3 rule. But to not confuse you, we'll just be calling it the Simpson's simple 1/3 rule. Now that we know which formula we're using, we can get to evaluating. But before we do that, one final thing, we need to figure out what is b minus a over our formula, so 2 or b minus a over 6. Now since b is 2 and a is 0, we get 2 minus 0 over 6, or 2 over 6, or just 1 over 3. So we can start applying our formula now. The area is approximately or equal to, in this case, since we're using a quadratic, 1/3 multiplied by f of 0, since it's the first endpoint, then 4 multiplied by f of the midpoint, which is 1, 4 multiplied by f of 1, and then plus the function evaluated at x is equal to 2. Now what we can do is we can just start evaluating. This is very simple. We get a is equal to 1/3, f of 0 is equal to 1, plus 4 times f of 1 is 4 multiplied by 4, and then plus f of 2 will be equal to 9. So now that we have our evaluating over here, we have everything plugged in, we can get to doing the arithmetic. So this becomes 16, 9 plus 1 is 10, so 10 plus 16 is 26. So this becomes the area is equal to 26 divided by 3. Now using integration, we can also verify this fact, and for those who know integration, I encourage you to try it on my own. You'll find that the area is also 26 divided by 3. This concludes our example for the usage of the simple form of the Simpson's 1/3 rule. And let's move on to our next example and our final example for this video, where we will be using the composite form of the same formula. Over here, our next example, the problem reads, approximate the area under the function x cubed plus x squared plus x plus 1 from 0 to 4 with n is equal to 4 subintervals. The first thing we can do over here, since the formula is not as trivial, is figure out how many spaces we're going to need and just write it out. So our area is going to be approximately b minus a, or 4 minus 0, divided by n, which is 4, but then multiplied by 1/3, then multiplied by f of 0 plus 4 multiplied by f of the next interval. So since its n is equal to 4 subintervals, we'll have the next one be 1. So f of a 0 plus 1 over here. The next one will be plus 2 multiplied by f of 0 plus 2 multiplied by the step size. So that's going to be 0 plus 2. Then plus 4 multiplied by the final one minus 1, since we're approaching the last one. And what we can do is we'll have 4 minus 1. You can also have 0 plus 3 over here if you're just evaluating it from the initial value. And then we have, for f is equal to 4, f of 4. Now you might have noticed this alternates, and it does based on whether it's an even or odd amount of steps away from the starting value or the ending value. So in fact, we can evaluate it if we know the step size from either direction, the f0 or the first one or the last one, and it will not make any difference on the values you get from this function. So it will be incredibly simple. If there is, let's say, one endpoint that is a little bit annoying to calculate with, let's say maybe pi, let's say it's from 0 to pi, we could just do it from 0 all the way until you realize what the step size is, so you know to stop and then have the final 4 and then the final just function with no coefficient inside the bracket. Now that we have the values figured out, we can start evaluating the function or the approximation. So the area is approximately, this will be 1 multiplied by 1/3 is 1/3. F of 0 is 1 plus 4 multiplied by f of 1 is 4 multiplied by 4. Then plus 2 multiplied by f of 2, that would be 8 plus 4 plus 2 plus 1. 12 plus 3 is 15 plus 2 times 15. Then the next thing we're gonna have is plus 4 times f of 3. Now f of 3 is 27 plus 9 plus 3 plus 1. This will be 4. 27 plus 4 is 31. And 31 plus 9 is 40. So 4 times 40. And then just plus the final function, where the final function evaluated at x is equal to 4, it's going to be x cubed, which is 64, plus x squared, which is 16, plus 4 plus 1. So 4 plus 1 is 5, 64 plus 16 is 80, so we get 85. This is our final value over here, and we will proceed to evaluate. This value again simplifies to a is approximately 1/3 multiplied by 1 plus 16 plus 30 plus 80 plus 85. Now where 80 plus 85 is 165, and this is 17. So area is approximately 1/3 of 30 plus 165 plus 17, and 165 plus 17 is going to be 182, plus 30 should be 212. 1/3 of 212. So the area is approximately 212 by 3. Over here we have our approximation, and it is not too far from the area, especially since we're dealing with a cubic function. The actual area is equal to 292 divided by 3, so the error margin would be 80 divided by 3, or around 26.6 repeating, or exactly 26.6 repeating. Now, this might seem like really bad, but in comparison, it actually really isn't that bad compared with the actual error. It's around probably in the 20% error margin, but this is also a cubic function and with something not optimized for cubic functions, and it's only n is equal to 4 subintervals. If we had n is equal to 8 subintervals, we would get much closer, as accuracy often increases when adding more and more subintervals, because the approximations and the margins become smaller and smaller and smaller, thus allowing for closer and closer approximations. So that's really about it for this video. If you're still here, thank you for watching till the end, and if you found my content inspiring, educational, or in any other way, please make sure to like, subscribe, and hit that notification button for more awesome videos just like this. And if you have any suggestions for the channel, please make sure to comment down below. Any suggestions, comments, or just anything you'd like to say, that will help my channel because I want to make it better for me and for all of you. Thank you so much for watching this video. See you in the next one, and bye-bye.